Oh, I think time it's now exact 4:30, so we can start the second part of our meeting today. And it's my big pleasure to present you Professor Bertrand Berche from University of Lorraine in Nancy in France. And I would like to say it's a very tricky problem to present Bertrand because he works in so many domains. I think it will be more easy to find the domains when you are not worked. I tried to do, but I didn't find. Finally. So just a short introduction, and I will cite some of domain when you contribute mostly. And so Bertrand got his PhD and habilitation in University of Lorraine in Nancy, and his principal field of research is study of the phase transition and critical behavior of various two- and three-dimensional systems under the effect of structural disorder, inhomogeneities, aperiodicity, or space confinement. Bertrand also did important contribution to the theory of spin transport in semiconductor, analyzing compounds with strong spin orbital coupling. And in a completely another field, he applied also the method of statistical physics to perform the analysis of the vulnerability of public transportation of major cities of the world. And also he worked in the biophysics. I also found some paper about DNA structure. And I also would like to cite interesting work with Ralph about the impact of research group size on their efficiency. And today it's another field, another thing, is mostly cosmology. And Bertrand will present us a lecture, Kalb-Ramond Classical Field Theory in Curved Spacetimes. So please, Bertrand.
Thank you very, very much, Elena. That's very nice. So you can hear me, I think. It's
yeah, we can hear you. Yeah.
Very, very nice introduction. That's yeah. So as you can imagine, I'm very, very happy to be online with you. We have very frequent online discussions with Jurko and other friends, and once and probably more frequently twice a week since the 24th of February, but even before, of course. But how to say, as it was said by Taras Brick in the introduction yesterday, this is really a great achievement to organize these Ising lectures online under the permanent threat of the Russian army, and so this is very extremely encouraging for the future that you're able to do that. As we were discussing before it started, really. Today I feel a bit like in Lviv because I am with Mariana Krasnitska. So she's no longer in my office because she's now in the garden. Maybe some of you have seen in the previous photo that she was outside. So hello, Mariana. She's working with me here in Nancy for a while within some kind of project that we have together because we have a collaboration since years already. And also I feel like in Lviv because in my bookshelves I have this book. So this is the selfie effect, so probably you cannot read, but I can read for you. This is the Ising lectures in Lviv, 1997 and 2017. So a new edition will be necessary, of course. And this book was made by 3 students at the time. I mean, Mariana Krasnitska was speaking about, Robin Direct from Coventry, and Petro Sarkanich. So this also is something which makes me feel like being in Lviv, more or less, almost at the ICMP. And I have many friends. I will not cite anyone, but I know a lot of people at ICMP where I would be happy to be able to come back physically soon. So concerning my talk together. As you said a bit, Elena, maybe I try to distinguish a bit myself, speaking about things which are not connected with the subject of the Ising lectures. In fact, I will not speak today about critical phenomena, not about phase transitions. So it happened to me already in the past, I think. But the Ising lectures, I think the first time I came to Ising lectures was probably in 2002, something like this. And at the time I spoke about disordered two-dimensional Potts models. That was strongly related. I saw that Viktor Dotsenko was also in the audience, and that work at the time was strongly under the influence, a strong influence of Dotsenko papers at the time. So today, yes, I will speak about something which is more exotic in a sense, but this is really for master students. Well, to tell the truth, it will appear in the Physical Review D, but it could appear in the American Journal of Physics or in European Journal of Physics. This is more master students exercise, you will see. And the second reason why I'm always trying to distinguish myself, this is the quality of my slides, which is probably a bit... Marianne, I saw you, yeah. So now you can maybe see my slide, I think. So.
Yes, we can see here.
So that's, okay, this is very unprofessional way of doing slides, but I hope you will be able to read my writings. So I will try to tell you about Kalb-Ramond field theory in curved space-time. So first I will discuss a bit the context of what is this Kalb-Ramond, maybe not familiar to everyone. You will see that that's a kind of extension of electrodynamics. So I will spend some time in the second part, a long time on electrodynamics, just to use Maxwell theory. I'm speaking about ordinary Maxwell electrodynamics, to use it like a guide, how to be able to build some other possible extensions, I would say. And Kalb-Ramond is one of these extensions. There are many, many, of course, depending on which symmetries you want to preserve, etc., etc. Then I will explain in the third section this Kalb-Ramond theory and eventually some applications in curved spacetime, because okay, Kalb-Ramond was introduced in the context of string theory. I'm not a string theorist, so what I know is essentially one equation that I will show, and that's all. But from these very tiny scales, that can also be connected to some geometrical properties of the global spacetime. So that's a connection to cosmology in a sense. So the context first. So as I said, there will be a strong link with electrodynamics. So if I just remind a few things about electrodynamics, I can consider a point charge, which I call E, which is living along its world line. And I call dx mu the line element, with mu one of the Lorentz indices. And for this system under an external electromagnetic field, I can write down the action. So the action contains essentially three parts: a kinetic term, here, kinetic energy, which is just the length of this world line up to some numerical factor there. Then there is a coupling of the charge E to the gauge field of the electrodynamic interaction, this A mu. This is the interaction. And then there is the free electromagnetic field contribution, which is the square of the stress tensor, F square here. And all these quantities are nicely written in terms of contraction of indices, the mu's here, and mu and nu here are contracted everywhere, just to get something which is compatible with special relativity. So you can generalize what was on the previous slide, considering now extended object. Instead of a point charge, here imagine a string, so which is an open string in that case, but okay, I call G the string. And when the string moves in space-time, instead of a word line, you now have a word sheet, I would write there. And this word sheet is described by an area element, which now carries two indices, mu and nu, say. So if you want to write an extension of the kinetic energy, you have to write something which is a double contraction on these two indices. So this is essentially the area of this word sheet, which is corresponding to the kinetic energy. Then when you want to write down the interaction of this string with some gauge field, because you have two indices for the area element there, you need a gauge field which carries also two indices, and some coupling which I call G, like it was E for the charge before. And then, of course, there will be a free field interaction, a free field contribution, not interaction, sorry, contribution to the action, which this is the Kalb-Ramond field. And since the gauge field carries two indices, the field strength carries three. I will come back on this later. So that's all I know about string theory, so that's not all. But just here, I have already a flavor of possible interesting generalization of electrodynamics. And the third aspect in the context where I will speak about This is connected to the geometry of space-time. So if I make a kind of crash course on differential geometry in 2 slides, I would like to mention the notion of torsion of space-time. Usually people know about curvature, but torsion is less famous, I would say, in physics. So the first thing that we need is the notion of a connection. So there are many ways to introduce a connection, but I will do this like physicists do usually. So the building objects that we need in a theory, for example, can be 4 vectors, that's and tensors, etc., etc. And 4 vectors, like this V, for example, under some arbitrary coordinate transformation, which goes from the x to the x primes, they have a given transformation law which is written there. So I can find the components in the new coordinate system in terms of the component in the original one. And this is extended to higher rank tensors. Second rank tensors, for example, are written there with the transformation which appears twice. But the problem with the vectors and tensors is that when you are looking at the derivative of a tensor, which carries 2 indices, so up and down, so that's a mixed tensor in a sense. In fact, it is not a tensor, because this quantity does not transform like it should if it was a tensor. And that's, of course, a real problem, because in physics we are mainly interested in writing differential equations. I mean, we know a system at a given point, at a given instant of time, and we want to see the evolution. And the evolution, of course, is measured by differential operators, time derivatives, etc., etc. So we have to repair this bad transformation law, I would say, and invent a new derivative. This is what we usually call the covariant derivative there with a nabla. And since this carries 2 indices, it should have something to do with the derivative. But then you add another piece there, and this other piece, which is you don't know what it is first, you demand that it is such that now with the new piece the tensor transformation law works. So it does at the condition that this guy, gamma, capital gamma, obeys some appropriate transformation properties. So this is what we call a connection. So this is a physicist's way. In fact, this is a component of a connection which is living in some, okay, not exactly in the manifold, but that's not a problem. So we do this like physicists. We write component equations. So from the connection now, we can define curvature and torsion, which are 2 properties. So as I said, curvature is well known, but I will start with torsion. So if you just look at the commutator of the covariant derivatives acting on a scalar field phi here, you just find something which is this expression. It is a difference of connection between for given position of indices that you can see there, multiplied by the derivative of the field. So this guy, which appears in front, we call it the torsion. This is a 3 indices, and this is a quantity which, obviously by its definition, is antisymmetric with respect to the exchange of mu and nu indices there. You can see this from this expression, obviously. If you look at the same commutator, so we are interested in commutators here because this has to do with parallel transport. When you parallel transport a quantity, and you do in one way in the mu direction, then in the nu direction, and then the other way, you see if the things coincide or not, and this is the reason of the commutator. But okay, this is a detail maybe. So when you act with the same commutator on the vector field now, you obtain a first quantity which carries now 4 indices there, because you have 3 indices and you contract with the force. So this is the usual curvature. And of course, the torsion, which was before, can still reappear there. So the curvature is given in terms of the connection by this nonlinear expression. Okay. So one of the most familiar theory of curved space-time in physics, this is a general theory of relativity, of gravitation, for which the choice of the connection is the Levi-Civita connection, which is just an expression in terms of the metric tensor and derivatives of the metric tensor. Mathematicians call this a natural connection. So this connection has, I write it like people do in this context, usually with a circle above. The circle means Levi-Civita connection. Okay, this is a specific choice for this guy. And with the choice, you can easily convince yourself that there is a symmetry when you exchange mu and nu, which means that the torsion given by this connection is 0. So general relativity is built from the beginning with absence of torsion. There is no torsion at all in this theory. On the other hand, there is, of course, a curvature, there is a Riemann tensor, and the Einstein equations are written on the last line, and there are usual Einstein equations written here in terms of some more contractions of the Riemann tensor, but again, that's not essential there. So what am I speaking about torsion, since it seems that there is no torsion in our world? So in fact, this is not absolutely clear, and there are possible extensions. That's always interesting to try to look at some extensions of known theories. So in fact, general theory of relativity is not the only possible theory, metric theory of gravitation, and there are some other possible choices of connections which can lead to zero or non-zero curvature, zero and non-zero torsion. And among these theories, some of them are empirically equivalent. For example, there is a theory which is due to von Weizsäcker, which is a theory where you have no curvature but only torsion. And this theory is built in such a way that it gives exactly the same results as the Einstein theory. So in a sense, being empirically equivalent is not that interesting. But some other theories may not be empirically equivalent and lead to different results. For example, if there is non-zero torsion and non-zero curvature, you have non-coincidence of the geodesic curves and the autoparallel curves in the differential geometry. So that's already a difference. And to make the link with what I said before, the Kalb-Ramond theory, as I mentioned, involves a 3 indices tensor, a third rank tensor, which is completely antisymmetric. And so it is more antisymmetric, I would say, than the torsion, which is antisymmetric with respect to exchange of the two last indices. But at least Kalb-Ramond theory has been considered as a possible candidate for torsion in space-time at macroscope, at astrophysics or cosmological scales. So that's the link between the two things. So my goal here will be to play with Kalb-Ramond theory and play with this in curved space-time for the reasons which I mentioned. But I have to tell in advance that I will completely neglect the back reaction of the Kalb-Ramond field on the geometry of space-time itself. So I will consider space-time fixed by some astrophysical objects, for example, a black hole or a cosmic string. And in this curved space-time, I will look at the simple structure of Kalb-Ramond field in static situation, because this is the simplest as a first approach. So that's the context. So now I said that that's an extension of electrodynamics. So maybe, okay, everyone of course knows electrodynamics, but there are some presentations which are maybe more axiomatic than others. And okay, there is one presentation in particular which I like very much and which I will use as a guide. So if I make a kind of summary of different formulations, one knows, of course, vector, tensors, or differential forms, formulations of electrodynamics. So, for example, in terms of vectors, here, for example, in a Euclidean space, okay, no curvature, nothing. So we have on the first line 2 equations which are written in the very usual way, which gives the relations of these fields in terms of the gauge fields. And they are often called homogeneous equations. And there are the 2 equations which involve the sources, electric charge, electric current. Okay, this is well known. Another formulation, which probably is better because we go from 4 equations to 2 equations, this is with tensors. So the first line corresponds now to an equation which is often called Bianchi identity, which is just a property of the stress tensor. And the second line is the equation of motion, which gives the field strength in terms of the sources. So that's more compact already, that's nicer. But still, this is in Minkowski spacetime. As it is written there, for example, the second equation is not valid in curved spacetime, for example. So there is still some work to do. It happens that the first equation is valid, but not the second. Now, if you go to differential forms, I will spend some time to explain this for those who are maybe not familiar, but differential forms, Maxwell equations are written in a very, very compact way now. That's still two equations, but very compact. One, which I've written there, df2, I will tell what it is 0, and the other d star f2 is mu 0 and something with a 3 there. I will explain this. I keep the constants. That can be surprising that I keep mu 0 c instead of putting 1 everywhere. But this is to make, you will see okay, it has some reason to make a difference between some fields in electrodynamics. So the language of forms is very nice because it gives some properties are topological properties and some others are not. And in fact, in the first equation here, this is what we call a topological property. I will try to explain what I mean by this. And the second one is not because there is a star. And the star, in fact, there are things hidden there. Metric is hidden in the star, and the metric is, of course, not a topological property. So a bit on tensors, vectors, tensors, and differential forms again. So if I want to define a differential form, one simple approach is to speak about the differential of a function. So I can imagine a function phi, which I can write in terms, let's say, in three-dimensional space, ordinary three-dimensional space, in coordinate, which are Cartesian coordinates, x, y, z. So the differential is written on this first line. And of course, I can also decide to work with, let's say, spherical coordinates in space. So the field phi is now a function of r, theta, and small phi. And I have the differential, which is written there. And if I compare these two expressions, in fact, I can look at dx, dy, dz like basis vectors. So dx, dy, dz, this is one basis of space. And dr, d theta, d phi is another basis of the same space. And the terms which are in front, I can understand them as the vector components. For example, dx phi is the component of the vector d phi on the vector basis dx. Like, in fact, dr phi is another component because this is expanded on a different basis. So generically, these vectors, in a sense, are one forms or differential forms of rank 1. So usually I will put, so generically, I mean, I write this way, one form. So I put the one at the top. Usually people don't do that because they know what they do. But I find it interesting to keep the rank of the form written somewhere. So I cannot put it like an index or an upper script. I put it above the symbol. So in fact, both equations are written like this. This is a contraction. The basis vectors are written like these contravariant elementary vectors. There is a contraction, so I need to have a covariant index on this quantity, which is just a component. So the contraction over alpha here in 3 dimensions, 3 values. And this contraction is the one form, I call it omega 1. And this belongs to some vector space, which is usually called in mathematics capital lambda 1 because of one form, living associated to the manifold. And the omega alpha here, which appears there, this is a covariant component, so it obeys the transformation law of covariant tensors. Then we can extend this, and we can create from this 2 forms, 3 forms, etc. So for example, a 2 form will be an extension of the previous one, but now written in terms of association of the basis vectors. So dx alpha, dx beta. So you need in front to have a component which carries 2 indices, which again will be a second rank tensor, covariant tensor. The 1/2 is just a normalization. And for some reason, which I will not explain, but we like to deal with antisymmetric covariant tensors. So in order for this expression to allow the simple contraction over the indices, I write there the antisymmetry. Omega beta alpha is minus omega alpha beta, and which demands, of course, that the same antisymmetry holds between the basis vectors. So the wedge, this symbol here is just to have in mind this antisymmetry. This is nothing very special, but so dx beta wedge dx alpha is minus dx alpha wedge dx beta. And then you can go on, write a 3 form, etc., etc. So the 2 form belongs to a different space. Lambda 1 and lambda 2 are different spaces, and of course 3 form belongs to lambda 3 and still another space. And with forms, you can do several things. So, for example, they can be integrated, obviously, because I come back to the previous expression. This is written like, this is ready to be integrated because you have a line element there. So this is one of the properties of forms. When you integrate a P form over a submanifold of dimensional P, dimension P, you get a scalar. So this simple property is very interesting to recognize what is a form in physics, in fact, and what about the rank of a form. So, for example, in electrodynamics, which is what we are doing there, you have that, for example, the voltage can be written as the line integral of the electric field. So this is a one-dimensional integral. So EdL can be understood as a one form. The flux can be obtained by the surface integral of a magnetic field. So BdS can be understood as a two form. And for example, the total charge in some volume is the integration of the charge density. So this product rho dV is a three form. So this is of course not very rigorous, but that's a way to have an idea of what can be a form in the theory, and more important, what is the rank of the form. Then we can play, as I said before, in physics we need derivatives, so we can also make a derivative of a form. But when we do that, we go from one space to another space, because due to the derivative, we increase by one the rank of the form. So this is why we call this an exterior derivative. Exterior because you will go from one space to another one. So imagine a P form, omega P. You define the derivative of the P form, the exterior derivative, as belonging to lambda P plus 1. There is a plus 1 due to this derivative. And for example, if it is a one form, you just use the standard expression. You have the form omega, you derive, you have two indices, so you need two indices. So this guy, of course, lives in lambda 2, while omega 1 was living in lambda 1. So this is the meaning of this exterior, the word exterior in exterior derivative. An essential property of this derivative is that when you apply it twice on any form, it gives 0. And this has very important consequences. So it means that when you have a closed form is a form which is defined such that its derivative is 0. So imagine omega p, which is such that d omega p is 0. So this is closed, and being closed, it is exact or locally exact if we want to avoid some problems of non-connected space, but I'll leave it okay. It is exact in the sense of derivative, it derives from some potential. So it means that there exists a p minus 1 form, which I call theta, such that omega is d of theta. And that's obvious because now d omega p is d squared theta, and d squared is 0. So automatically you get the fact that the closed form is locally exact. This is one thing that we can do with forms. Okay, one thing is to integrate them. Another thing is make derivative. There is a third property which is not obvious a priori, but which is essential for writing actions in physics. And this is what we call the Hodge dual, or the star product. There are various terms for this in the literature. And for this, I need to speak about the volume form first. I mentioned, if I come back to the previous slide, if I was in 3D, I mentioned the case of the density, of the charge density. I integrate there over the volume. So generically, because that was the volume in 3D, for example. But generically, if I am in a d-dimensional space, I define the volume form as something which is the maximum form. I mean, it contains dx1, 2, 3, up to d for the d dimensions, which correspond to the d coordinates in the space that we or space-time that we are considering. This is maximal in the sense that if I take the wedge of any other d there, for example d2, I will have the antisymmetry which will allow me to move this d2 backwards until it arrives close to this d2, and dx2 wedge dx2 is 0 due to an antisymmetry. So this is the reason why this is maximal. And in front, we put the square root of the metric tensor, of the determinant of the metric tensor, just to be able to have this volume properly defined for arbitrary manifolds, not only Euclidean or Minkowskian. So this number can be important. And once you have the volume form, you define the Hodge dual to be something which, applied to a given form, completes this to the volume form. So for example, imagine that we are in three-dimensional Euclidean space. So there, the volume form is a third rank form. If you start from a 1 form, omega 1, it lives in lambda 1. So then the Hodge star applied to omega 1 will be something which lives in lambda 2. So it will carry 2 indices, and the definition is given there. This is in such a way that you probably complete omega 1 by star omega 1 to have something proportional to the volume form at the end. So the ingredients which appear there are, again, the metric tensor, or the determinant of it, the Levi-Civita symbol, which is a completely antisymmetric symbol with the right number of indices depending on space-time dimension, the contravariant instead of the covariant. You see that that's the covariant in the definition of omega 1. That's the contravariant which appears there, and you complete the basis vectors. So once this is done, you have an essential property which is written there. Omega 1 wedge star omega 1 is proportional to the volume form, and the proportionality is just a Lorentz contraction. So that will be essential for to know how to build actions properly in physics. And the relation with topology, this is something which I will discuss during the talk. I will tell you this is a topological relation, this is not, etc., etc. But essentially, when star appears, when the Hodge appears, it means that the metric is hidden and things depend on the coordinates. So this is an example. So maybe there is maybe no need to discuss. Oh, okay, that's fast. I can. This is an example of something which is not a topological relation. This is, for example, Laplace equation. Imagine a two-dimensional space with coordinates which are Cartesian coordinates x and y. If you write just the Laplace equation there, so by default in this choice of coordinates, the metric tensor is obvious. Okay, you have a given equation. Now, if you write it in, I don't speak about the boundary conditions, etc., etc. I'm just writing the equation there. Now, if you write the same equation, but now in polar coordinates, of course, we know that there is appearance of this factor here, which is a metric factor because it's associated to a component of the metric tensor in this coordinate system. So the equation is not the same as this one. Physically, we describe the same guy, but this is not the same equation. It means that the function, when we solve for given boundary conditions, the function in polar coordinates, we have something which is a function of r and theta, but which is not the same function of x and y. This is a function once you come back to r and theta. So I mean, in physics, very often we write phi of r theta is phi of xy, but because we think in terms of phi as an object. The object is, for example, the scalar potential. But the function itself is not the same function, of course. So mathematicians would not write phi r theta equals phi xy, okay? And the way to reconcile mathematicians and physicists, this is when you have a topological theory. So if it was the case, I remind you that this is not, but if it was the case that Poisson equation was topological, we could draw the manifold, the 2D manifold, and have two coordinates, which I call, I don't know, square and circle there. I would write the equation in terms of square and circle. I have a certain form, and then I give the solution, which is this. And if then I'm drawing some other coordinates, whatever they are, the Laplace, the operator would have exactly the same structure, so the function will be exactly the same. So we will see later quantities which will be like these and quantities which will be like these, in fact. So we know enough on differential forms. So now I can go on with, as I said, the axiomatic presentation of Maxwell electrodynamics. Now in Minkowski space, so in M4. I have essentially two postulates. So one postulate is that I assume the existence of a two form, I call it F. Of course, this will be the Faraday tensor. And the existence of a three form, I call it J, and it will be the source, the current, the electric sources of the matter contribution, let's say. And I assume that these are closed forms. So this is the postulate. It is written there. So dF is 0, dJ is 0. So the second, by the way, is charge conservation. So we like it very much. And because these are closed forms, they are exact. So it means that for f, there exists a one form such that f is the derivative of the one form. And for j, there exists a two form, which is just such that j3 is the derivative of the two form. So the first one is the Bianchi identity, and the second one here is the equation of motion. So the postulate is there, in fact, because here it is a consequence of the postulate. There is nothing new, it's just a rewriting of this. Okay, these are, as I said, topological equations because there are no star, nowhere there. There is no metric tensor hidden or whatever. But this is not a closed system of equation because we don't know if there is some relation between f and g there. So that's something that we have to add to the theory, which we usually call constitutive relations. For example, you all know that in the empty space, usually we define, let's say, the vector d in electrodynamics, the displacement field, the vector d, like epsilon 0 vector e. So this is a constitutive relation. So we know also constitutive relation to see whether there is a link between these two guys. Otherwise, these two equations are not enough to solve the theory. I can find f, I can find j, but I don't know how to relate these two. Okay, so for that, I can, for example, take a second postulate, which is the form of the action, which I have written there. So as I know already some physics, so I know from, for example, Schwarzschild, Lagrangian of electrodynamics, that the free field is something which is quadratic in the Faraday tensor. So here I'm looking for something quadratic in the two form f. But if I take f wedge f, okay, I don't know what it is, but this is maybe not Lorentz invariant, and in fact it is not. On the other hand, if I take f wedge star f, this is good, because as I told you before, when you take a p rank form wedge the star of another p rank form, you have something proportional to the volume form, and with in front a Lorentz contraction. So this guy is obviously constructed to be Lorentz invariant, and even more, because in fact this is even true for arbitrary coordinates and spacetimes. So this is even generally covariant under any kind of diffeomorphism. So this is for the free field. And then if you want to connect the free field to the matter contributions, you have a one form which is associated to this two form. This is the one form which I have defined before as the gauge field, in fact, a gauge vector. And you have to take the wedge of something which is a star of a one form also. So in such a way that, again, this will be Lorentz invariant. So you see that here I have star J1, and here I had J3. That's not the same one. That's a kind of curly J, and that's, I don't know, a capital J. But clearly there will be a link between star J1, which is a three form, and J3, which is also a three form. Remember that we are in four-dimensional space-time, which means that the star of a one form is a 4 - 1, so it's free form. So this has exactly the correct structure to make a theory. And I don't need anything else. The theory is Lorentz invariant, even generally covariant. It is gauge invariant. That's very easy to show that this is conserved if you make a modification of the gauge one form there. It is parity and time reversal symmetric, etc. So it has plenty of nice properties. So one postulate there, a second postulate, I should have put a box there because this is really a postulate. And then you just apply the minimization of the action, the Hamilton principle. So the variation, you just apply formalism of differential forms. So I don't discuss about the detail there, but the variation of the action when I change A, the one form A, to A plus some delta A. So this is the variation quantity. And you can easily write it in terms of this. And if you demand that this should be 0 for arbitrary variation, you have the parenthesis here, which is 0. This is the parenthesis, which is the equation of motion. And now if you call what is in front G, the derivative of G2, and you call what is on the right-hand side, the J3, which is the current, you recover the expression that we had before. So that's a link, which is again written there, between the G2 form and the F2 form. This is a constitutive relation. So this is written there for arbitrary space-time, but it depends on the metric through this star which appears there. So that's in M4. Now, if we are in just in 3 dimensions, just to compare and to come back to the reason why Laplace equation or Poisson equation are not topological equations, because they carry the star somewhere. I can just make a side remark there. In 3D, we could call the 2 form F, the Faraday form. We can define it in terms of the electric and magnetic forms. So you might remember from the line integral that the electric field is a 1 form, and the magnetic field is a 2 form. So that's the definition of F. The minus here, they are just there because I'm usually using the plus minus 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 signature for the metric tensor, and it depends on that. So the minus is not very important. But I need them in order to have the correct matrix there for the Faraday tensor if I put the correct components of electric and magnetic fields. So this is the definition of the 2 form F. If I write Bianchi identity, which is there, I collect 2 equations. And if you look at this, it looks very, very similar to the Maxwell equations in vector notations. Divergence of B is 0, and dTB plus rotor of E is 0. So that's the way to write divergence and the rotor of the curl in this formalism. Then from this, of course, you find the definition of B as the rotor of the vector potential, and the electric field as minus gradient of the scalar potential minus dt and the vector potential. So that's for Bianchi identity or for the homogeneous Maxwell equation. And the equations of motion, you do the same. You call G2 something which is connected to the displacement 2 form and the magnetic excitation 1 form, D and H. You give the definition of the current 3 form in terms of the charge density and charge current, and you obtain 2 equations, one which is Gauss equation in a sense, which is divergence of the vector field D is rho, and the other which is Ampere law, the rotor of H minus dt of the vector D is the current density. And so the Poisson equation, for example, you take just the electric sector. In the electric sector, you cancel this, you just have this guy, and you write the relation between G and F, this relation where we had the star product which was there, you write it here, and just after 1 line, you get that the star of minus d phi is this guy. So this star of D gives, in fact, the Laplacian. So there is hidden in the Laplacian the Hodge product, and this is why there are metric factors there, and this is why this relation depends on the choice of coordinates. Okay, so if I summarize what we have done for Maxwell electrodynamics, one postulate was there. From this postulate, we have built Bianchi identity, so we have built the 2 form and 1 form that we know. Second postulate with the action, and from the action we have a link between the 2 form F and the 2 form G, and we have the equation of motion. When you do this in tensor form, we have the Bianchi identity in terms of these 3 index tensor expression that we know. We can write the action, but you see that in tensor formalism, so you recognize probably the tensor, then the Lagrangian density there, but you have to put a square root of minus j if you want to go in arbitrary spacetimes. So this is something new. And for the same reason, Maxwell equations now are not the same as in Minkowski spacetime. They carry this. And so I have to take care about that when I'm working in tensor formulation. And when I'm working in vector form, that's even worse, because here this is written only in flat spacetime. No, okay, there are some extensions which I will not discuss. I have this on the slides, but I will not have time to discuss. But there are some extensions of the divergence and the curl operators in curved spacetime. And some things I just write there, some unsolved issues. I should not write unsolved. It's perfectly solved, but unknown from the students, I would say. These very standard notations that everyone knows in the empty space, for example, Minkowski space or Euclidean space, In fact, they cause severe problems because E and D do not have the same transformation properties by change of coordinates. So D equals epsilon 0 E is impossible, at least not with epsilon 0 a constant. And H is mu 0, 1 over mu 0 B is impossible also. So, but this is something else. Okay, so I said that now we want to possibly invent new theories. So there are many alternatives to Maxwell theory. So here I've written simple because I keep, in all these theories, I keep this definition for the stress tensor, the Faraday tensor. I could even, relax this constraint, but these are even more complicated theories. So this is why I say simple, because automatically Bianchi identity is satisfied. So I automatically have the same set of first Maxwell equations, but we play with the equations of motion. So in Maxwell theory, the Lagrangian density was this one. Okay, we mentioned that. So we could add, for example, a term proportional to the square of the gauge field. This is a mass term, and this is what we call Proca theory. So this theory is interesting, but non-gauge invariant, for example. So it's very interesting in, say, in superconductors, for example. We can add to this another kind of contraction, which is the contraction of F with the dual of F. It gives dual theories of electrodynamics, and this one, for example, is not PC symmetric, but that's some extension, some possible extension. We can play with Born-Infeld. Born-Infeld is instead of the square of F, that's a strange quantity there, but which is there just to remember relativity, in fact. And this leads to nonlinear equations of motion. The reason for Born-Infeld, okay, I will ignore the discussion on that, but it was from the early 20th century. You can consider, for example, Bob Podolsky. Bob Podolsky, instead of having the square of F, you have the square of dF now. So that's higher order equations of motion, which are also interesting for some reasons. You can invent, for example, Chern-Simons theories, which are essential for, let's say, quantum Hall effect, for example. And they are not quadratic in F, but in AF, if you want. This is ADA. DA is associated to F. And with the contraction there, which is with the Levi-Civita symbol. So that's also have some interest, etc., etc. And Calb-Ramond is also an extension, as I mentioned initially. Just I'm increasing the rank of the tensors there by 1 unit. So instead of a second rank tensor for F, I have a third rank tensor for M. And instead of a first rank tensor for the gauge field and the source terms, I have 2 indices there. Okay, and there are some other magnetic monopoles, non-metric theories, etc., etc. So as I said, Kalb-Ramond is a very simple extension. And I will follow exactly the same lines. So I can be a bit faster than what I've done for Maxwell. But so in the Kalb-Ramond theory, I will start from the same thing. I assume the existence of a 3-form M and a 2-form S, which are 2 closed forms. So you could tell me that's the same as before with Maxwell, because Maxwell I said F2, so that was a 2-form, and J3, that was a 3-form. But in fact, I reversed the order of these. The source term will be the 2-form, and the field strength will be the 3-form. Okay, so that's not just the change of the names of the symbols in a sense. Okay, but that's a postulate, first postulate. So of course, since these are closed forms, they're exact and they can be written as the exterior derivative of something. So the first one again is Bianchi, which requires the introduction of a second rank antisymmetric tensor for the gauge field. And the other one is the exterior derivative of one form and will be the equation of motion. And I call everywhere S for source term. This is a quantity which replaces the currents or the charges. Then I assume a Calbrahman action, but we know the game. We have to take a form wedge star of a form of the same rank. So that's very easy. I want something quadratic. If I just follow what we have done for electrodynamics, quadratic in the strengths, so M3 wedge star M3. And then I have B2 already in the theory because of Bianchi identity. So I have to couple it to the wedge of a 2-form in such a way, the wedge of the star of a 2-form, sorry, in such a way that I have again something Lorentz invariant. So again, this guy has good properties. Invariant under arbitrary transformation of coordinates, gauge invariant, etc., etc. PC symmetric, PT symmetric. And if I write the variation of the action, here I get the equation of motion. Very simple again. So these equations, so this one which I have now in the box and the first one which is in the box there are the two equivalent to Maxwell equations. So since this is star m which appears, I can define star m as being a one form. Still, like before, we are in four-dimensional space-time. So the wedge of a three form is a 4 minus 3. This is a one form. And I can introduce the curly s to be minus star of the capital S, just to give back the equation of motion. And if I write the same in tensor language now, I could do exactly the same. There are more indices. This is a bit more heavy, but not too much. So I define the field strengths in terms of the gauge field. The gauge field is itself an antisymmetric second-rank tensor. So B mu nu is minus B nu mu. So the only way to define antisymmetric tensor, which is given by 3 indices from the derivative of this one, is by this combination. Okay. So these two are antisymmetric with respect to the exchange of any of the indices. So then we have the Bianchi identity, which follows automatically, but now it is written that way, which is not very difficult. You see, you have kappa, lambda, mu, nu, and you have a plus or a minus, just depending on the number of permutations between these indices. That's very simple. You assume an action as before, so the action is a full contraction over the 3 indices there, and this is a full contraction there. We see that this is Lorentz invariant, and if I incorporate the determinant of the metric tensor, it is even generally covariant. And the equation of motion written from the variation of this action, I get this expression. So this is a charge which I have introduced arbitrarily there. That's just like the electric charge. 1 over square root of g, because we're in arbitrary space-time, a kind of derivative there of something which is not simple, and the source term there. And automatically, due to the symmetry properties of M, we have a charge conservation, which is also something a bit more complicated than in Maxwell theory because of the appearance of one more index. So that's also tempting to look at this in the vector language, because we are used to Maxwell equations in vector language. So we will see how these Kalb-Ramond equations written in vector language are similar to Maxwell in a sense. So like before, I introduced a definition for M3, like I've done before for the Faraday tensor in terms of electric and magnetic field. Remember that I had minus signs because of the choice of the signature, and here I don't need, because we have no experience with these fields, so I can call them however I want. Before I had to put the minus because everyone knows in which direction an electric field goes. If I say that the electric field is going in the direction of a positive charge, you will tell me no, it's escaping from a positive charge. So this is fixed. We don't know that for Calb-Ramond, so we don't care. So I don't put minus anywhere when I don't need. So I introduced just a 2-form R and a 3-form K. So I put this for Kalb and Ramond. Okay. So this is the definition of M. The fact that this is closed implies, in terms of these 2 and 3 form, 2 equations which are there. And from these 2 equations, I can define Kalb and Ramond fields here in terms of potentials. And you see that you have a potential 1 form and a potential 2 form now, which I call phi and alpha, which looks like the phi and the A of electrodynamics. So if you write this in terms of vectors, you have this. So this is a Maxwell equation, a Kalb-Ramond equation, but similar to Maxwell equations with B and E, electric and magnetic field. And this is the definition of the fields in terms of the potentials. Okay, you can check that this is gauge invariant, etc. There is no problem there. And now for the dual of M3, this is N1. I introduce also a 1 form and a 0 form. So for R, I use T here instead, and for K, I use lambda instead. And I do the same for the sources, which gives me simple equations in differential form there, which have their translation in terms of equations of motion. So the rotor of t is some density sigma, and the gradient of lambda plus 1 over c dt of d small t d time over the vector t is the other sources. So you see that in Calb-Ramond theory, these are extended sources which the equivalent of the current and of the density are two vectors in this case. So these equations are the equivalent to Maxwell equations in the Kalb-Ramond theory. And the constitutive relations that we had before are these simple links between R and T and kappa and lambda, like we had in the... So this is written in the improper way, exactly like when I've written the relation between D and E, etc., saying that the transformation properties are not satisfied, etc., because again, the star is hidden somewhere. But here in Minkowski spacetime or Euclidean spacetime, the determinant of the metric tensor is 1, so you don't see it, 1 or minus 1. Okay, so this I will skip. This is just to say that we can do better. Here I've written the equivalent to Maxwell equations in flat spacetime. We can do better and write them in arbitrary spacetime under proper definition of the time derivative, divergence, and the rotor. But okay, I will skip it. And now I go to the applications, the last part of my talk. I hope that I'm on time. Yes, I'm on time. So I'm looking at what happens in curved spacetimes. So this section is essentially exercises. You know, you have made the class and in the lecture room, and now you are doing the exercises with the students, and that's a good moment to do that. So for that, I will take the illustration again, just to have some intuition of what happens in the case of Maxwell theory, and even in the simplest case of electrostatics in Maxwell theory. So for example, imagine that I want to find the fields, the electrostatic fields in Schwarzschild spacetime. I mean, I have a black hole that's most famous, maybe curved spacetime. So imagine a black hole. I take Schwarzschild coordinates. So the line element, the square of the line element is written there, as we know. So this is here in what I call V4. This is a way we usually denote the manifold, the pseudo-Riemannian manifold of general relativity with curvature, but no torsion, as I said before. So that's its name. Like M4 is for Minkowski. V4, V, I don't know for who, in fact. This is not Einstein, this is not Riemann, so I don't know. Okay, that's the square of the line element. And I will use the tetrad formalism, which means that instead of playing with these vectors or square of vectors there, I will make a change of basis going to the tangent space, and I'm considering a Minkowskian locally Minkowskian tangent space. So this is at point X, the tangent space of M4 can be chosen as being obeying to M4 metric, so Minkowski. And Minkowski is with a metric which we usually call eta. So eta is 1, -1, -1, -1 on the diagonal. That's all. And of course, G mu nu is different. This is 1 minus 2m over r on the first entry, then etc. etc. Okay. So in this locally flat space-time, I call E0, E1, E2, and E3 the basis vectors. This is what we call Cartan frame. So Cartan is Élie Cartan, the French mathematician, which was professor in my university. Using the components of the Cartan frame, we can find a link, a relation between the Minkowski metric and the curved spacetime metric. So we can, often we call these the local coordinates, the mu nu, and the AB, we call them the non-holonomic coordinates. And there is a way to go from one to the other. So this is something which people who are used to differential geometry know very well. We call this Vierbein or tetrads in 4 dimensions, and okay. And the thing is that in the Cartan frame, since it is Minkowskian, special relativity holds there, and that's essential. So because this is the case, we will write the first equation of motion. Remember that the first equation of motion was differential exterior derivative of d2 is rho 3. And I integrate the exterior derivative of d2 over some 3 volume, and I do the same for rho. And of course, there I can use Stokes' theorem and go from the volume to the surface integral. And here, this is the result of this integration is just the charge which is enclosed by inside this volume. So if we have a Minkowski symmetry in the Cartan tangent spacetime, we have spherical symmetry there, which means that we can write the two-form D2 as something which has only one component on E2, E3, and this only component depends only on the distance r. And if you change from E2, E3 to d theta, d phi as before, you find a relation between d2, 3 and d theta phi, which is this relation. So now I know that this integral is Q. Now I can make this integral, which is the surface integral. And the surface integral now is just trivial. I just get here the solid angle and the integration, which gives me 4 pi. So from this, it follows two things. First thing, in the Cartan geometry or spacetime, we find something which is like we have usually in Minkowski spacetime, I mean in Euclidean space, Q over 4 pi r square. And in the local coordinates, which means in V4, we have this expression for the two-form D, the only non-zero component of the two-form D. And this is why this is the equation which I call topological, because you will see that this will be unchanged even when I will change the coordinate system. Then, if I want to have the electric field, so I spend a bit of time on this example, but the rest is following exactly the same line. So the electric field, you get it just from the action. Remember the star of the Hodge operator applied to the Faraday form, in fact. So now that's written the other way. If G2 was the star of F2, it means that the star of G2 is F2 up to the constant. So I can find the electric field by taking the star of G2. And you might remember that in the Hodge star, we had the square root of the determinant of the metric. We had the Levi-Civita tensor, antisymmetric symbol, and we had the contravariant components. So we just play in the present Schwarzschild coordinates with all these quantities which are written there, and just a bit of calculation gives you that the electric field in the local coordinates is just the ordinary electric field. So it seems to be strange, but this is like Schwarzschild or Euclidean seems to be the same. In fact, R has a different meaning in both. I mean, R here is measured the quantity which enables to measure the surface of the sphere. But okay, I don't enter in the interpretation of the geometry there. To show you that what is isotropic, what is topological and what is not, I can give another example of the same black hole, but now in a different coordinate system. This is what we call spherical isotropic coordinates. So the metric, the square of the metric element is there. It's a bit more complicated. You have a rho instead of R, so that's something different. But you do the same. You go to Cartan frame. You take this determinant of this metric. You take the metric. The components of the metric tensor. We calculate these the same way, and magically we find exactly the same as before. But when we do this for the electric field, we find something which is different, which is this expression is not the same as we had before. And now we do the same for Kalb-Ramond fields. We know the principle. We first look at the topological expression, then to the equation of motion. So Kalb-Ramond field, I said that it could be connected to torsion in some sense. So that's interesting to consider geometries where torsion could appear. So there is an example for that given by cosmic strings. There are various types of cosmic strings. Some of them have only curvature, some of them have torsion, and some of them even have angular momentum. So the illustration there for the Kalb-Ramond field is in the case of a black hole space-time, which is pierced by a cosmic string. Imagine you have the black hole and the cosmic string, which is just crossing this black hole through the center of the black hole. I don't know if it's possible, but it doesn't matter. It's the only way to get the symmetric metric also. Anyway, the metric in Schwarzschild coordinate is the same as before, except that there is an alpha square here, which is connected to the curvature of the cosmic string. So due to this string, we have a cylindrical symmetry now. And when we write the equivalent of Gauss theorem, which is now more similar to an Ampere theorem, and we understand that the string, and when we make a line integral around the string, it looks very similar to a circulation and to an Ampere theorem. So I define the flux at the basic quantity instead of a charge for the cosmic string. And I calculate, assuming cylindrical symmetry like before, the only non-zero component of the form T in the Minkowski coframe or in the local coordinate system. And in the local coordinate system, I find the flux phi divided by 2 pi. Then I take the Hodge of this to find the R, the component of the R2 form, the Ramond 2 form. Okay, that's my notation to call it R like Ramond, but okay. Okay, you do the same as before. That's easy calculation to use a Hodge, and you get a given expression there. Okay. Now, if I want to show again what I understood in terms of topological or not, I can play with Israel coordinates. These are different coordinates, but still to look at a black hole pierced by a cosmic string, an ordinary cosmic string. The thing is that in Israel coordinates, you mix up the radial and the time component. You have a part here which is not diagonal, and that's very interesting to look at what happens with non-diagonal term. You do the same. You find the same expression for the field T, but you find a different expression for the field R. So when local coordinates are different, R experiences these local coordinates. T does not. Remember that T is more like D, the displacement field, and R is more like the electric field. Okay. So as I said, cosmic strings have lots of possible applications, and there is a wide variety of cosmic strings. And among them, I can consider 3 very interesting ones. The wiggly string. Wiggly string is a string which is not straight line. It's like this kind of string. And in the wiggly string, you have a coupling between t, time, and rho, the radial coordinate. There are chiral strings for which you have a coupling between the angular coordinate and the z coordinate along the string. And there are also spinning strings, for which there is, this is those which carry an angular momentum, for which there is a coupling between the time and the angle. So all these 3 cases, I think, are interesting. So now I get rid about the black hole, because in fact the black hole was transparent in the previous calculations. So I keep only the string. For the wiggly string, so the metric element has been calculated. It has a very, not easy expression, but there is a coupling between t and rho, the radial distance. And you find again, the object is not the same, but still you get the same expression for t, and r you get something else. Okay, good. Then the chiral string. So the chiral cosmic string is very, very interesting, because this is one which corresponds to torsion, non-zero torsion. This is something which is similar to a dislocation in a material. So maybe you know a bit about Volterra construction of topological defects in materials, and I will explain a bit this. Imagine that you have a cylinder, which I show there, and imagine that you cut along a radius of the cylinder. You just cut everything. You take your knife and you cut it completely, and then you make a shift of one part of this cut and not of the other one. So it introduces, of course, if you make it really, you will introduce a very, very strong stress on the axis there, and this stress is associated to non-zero torsion on the axis. And so this is what would happen with what we call in materials a screw dislocation. And in that case, people who are doing elasticity theory in materials, they introduce what they call the Burger's vector. And the Burger's vector is exactly this coupling between z and phi. So when you do that, on the top of what we had before, we still have a t component and a 0 component for r. But there is an additional component which appears due to torsion, which is the rho phi component. So that's something which is new and which is very interesting, and which is completely associated with the existence of torsion in the manifold. And eventually I mentioned the spinning cosmic string. So now there is some angular momentum, which is, let's say, small a here. So this is a string which is rotating. And the coupling is between t and phi. So like before, you get the phi component of t, which is always the same, the 0 component of r, which we know already. But now there is no other component of r, but we generate the other field, the kappa field. And this kappa field is like a magnetic field. So like you are in the situation now, you have the equivalent of the D field of electrodynamics, the E field, electric field, sorry, and the kappa, which is the magnetic field of electrodynamics. So that's a lot of fun that we can do with this. I don't know how much it's interesting in the sense. Probably it would. Measuring these fields would be a way to know whether we are in the space-time of a cosmic string or another topological defect somewhere. But okay, I don't know if Kalb-Ramond fields can be measured somewhere anyway. So finally, the conclusions. I hope I'm more or less on time. There are lots of things that we can investigate further and which are really interesting. As I said, I'm at the level of electrostatics, so that's really undergrad physics. And of course, there are all the extensions that we can do for the theories of electrodynamics can be done there. But there are also very fundamental questions. For example, those of you who are familiar with this tetrad, maybe you noticed something which is very peculiar. When you write the equation, the link between the curved spacetime tensor and Minkowski spacetime tensor, this is an equation like this. And the metric tensor is usually considered as being symmetric. So it carries in 4 spacetime dimensions 10 different indices. And the components of the tetrad fields, there are 4 components there and 4 for this index, 4 for this index. So there are 16 altogether. So we have 16 quantities fixed by 10 constraints, which means that we have freedom. And the freedom that we have is 6, a number of 6 in components. And this corresponds to the 3 boosts and the 3 rotations in Minkowski spacetime of special relativity. So that's very interesting to make clear that we maintain invariance with respect to rotations, boosts and rotations in the Minkowski tangent space. And yes, indeed, we can show that this is okay. We can also, in the same spirit, look at arbitrary cylindrical symmetry with arbitrary tetrads, and okay, some calculations can be done. And then to speak about some further investigations, of course, the first thing maybe is to look at non-static problems, as I said before, because Kalb-Ramond field can propagate. And that's so we can write the wave equation, which is a wave equation which looks in ordinary space-time, looks like wave equation for electrodynamics, except in terms of polarizations. There are much more possible polarizations than in the case of electrodynamics. So there are plenty of things to investigate there. And also, maybe the most important, but I don't know how to do, I've totally neglected the back reaction of the energy of the Kalb-Ramond field on the space-time metric. But of course, at the end, this is what we would need. So that's essentially what I wanted to tell you. So I will stop there. I hope that I am on time, and maybe I will stop sharing my slides. So thank you very much for your attention. I hope I was not too long.
It's okay. Thank you, Bertrand. It's very, very nice presentation with very beautiful physics.
Thank you.
So now the paper is open for discussion. You have time for few questions, but anyway, I think it's the last presentation. So if you would like to discuss, I think we can continue to discuss. So who is the first one? Please, I don't know who is Yar.
Yuri Yerenko.
Okay.
Thank you. First of all, thank you very much for a very interesting talk. And I'd like to ask you about the symmetry properties of the theory you presented. You mentioned the symmetry problems in the last slide, and you start your talk with classical electrodynamics in Minkowski space, and then Minkowski, this theory has asymmetrical disrespect Poincare group, which is the isometry group of Minkowski space. And according to the Noether's theorem, there are conserved quantities. And the U theory is generalization of this theory of electrodynamics by means of rising of order of forms when we use the language of differential geometry. U theory describes the electrodynamics of extended objects such as string. String is extended object comparing to the point like charge as is classical electrodynamics, standard electrodynamics. What do you say about the symmetry properties of this Ramond-Kolb theory? Because, for example, in you write the action principle, it is, for example, action principle there is for curved space on flat space, and this there exists symmetry group, and generally my question is about the symmetry properties in the context of conserved quantities.
Yes, thank you very much for your question. If I understand properly, but in fact, to tell the truth first, I think I don't have the answer to your question, but I will try to tell you okay how I understand the things. That's true that in terms of when we are in Minkowski spacetime, that's still the isometry group. That's very clear. But the point on conserved quantities there, as I understand, associated to Noether's theorem, for example, would be the conservation of the charge. In electrodynamics, for example, the charge is conserved because of U1 symmetry. And U1 symmetry leads to the conservation of a first rank tensor, which we call the current, the electric current. And the question we can ask in Kalb-Ramond, we have two indices. And the conservation equation I've written somewhere, maybe I don't know if I have to show it again, but in tensor form, this is very similar to yes, I will try to share again, just to show, maybe I can. So that was a slide. On my screen there, this is the conservation equation that we have. So of course it's very tempting to ask whether there is a symmetry which is such that the Noether conserved current associated to the symmetry, the conservation equation, takes this form. And this, in fact, I don't know. And I don't know because I start from the conservation equation as an assumption. Maybe you might remember that I start there with this equation, which is the conservation equation. So I did not have to investigate. I postulate that it exists, but I absolutely have no idea about the symmetry which would be behind and which would lead to this. So I don't know how I understand. I answer to your question, but for sure there is probably some gauge symmetry, global symmetry hidden somewhere, which leads to this, or in terms of tensor form, which leads to this expression. I have no clue how to do this because this guy carries two indices. There is only one which is contracted in the conservation equation. Okay, so I cannot answer. This is like the formulation which I have taken. That was the same for electrodynamics. In Maxwell theory, I started from the very beginning with the assumption that there is a conserved charge. Here, it was there. That was Maxwell, you see. So I have already used this as a postulate. Of course, this is not the only way to do electrodynamics. You play with the postulates that you want, but I have these as postulates at the beginning. So I have not used Noether's theorem to prove this. There we know how to do this. We know that this is U1 gauge theory. For Kalb-Ramond, I don't know. And as far as I remember, it is not discussed. The paper by Kalb and Ramond this is an old paper. This is 74, I think. And I think it was not discussed neither. But probably people in string theory should know that because they are used to work with these extended objects. So I'm sorry that I cannot give a better answer. I can only confirm that this is probably a very good question, but I ignore the answer of that.
Okay, thank you, Bertrand. Next question is Ralph. Yeah.
Okay, charge conservation is arise from the simple rule that double exterior derivative vanishes. And conservation laws arising from the neutral symmetry is more complicated.
Yes.
Okay, thank you very much.
Thank you.
Okay, thank you. Ralph, you wanted to ask the question? Ralph?
No, I didn't have my name up.
I think it's Reinert. It's Reinert.
Okay.
Yeah, I say hello,
I'm sorry,
Bertrand. Hello, Bertrand.
Hi,
so it reminds me to my student time of some lecture of Turing or so I have heard. So I have it's not a simple question as I see, since it belongs to the future program, I think. It's a question, what can you say about the angular momentum of the electromagnetic field in this case? You see, you have a separation into inner angular momentum and an orbital angular momentum in classical field theory. And now if you go to a space with torsion, first, can you make this diversion in these two parts clearly in the new theory? And goes the torsion of the space into this definition of the angular momentum?
Okay, thank you for the question. So the question you are asking, I think, is answered already by Hale. You know, the papers maybe by Hale in 72, 73, 74.
No, sorry, yeah.
So, okay.
I know the name, yeah.
Okay, but there were not the first. First, before them, there were Keeble and Sciama who started to make a gauge theory of gravitation. And they were the first one to extend, as far as I know, to extend a bit of general relativity in this direction. Then Hale really looked at what happens in Cartan spacetime instead of, which means curvature plus possibly torsion. And when you consider a spacetime with both properties, geometric properties, you can write the minimization of the action like we do in Einstein theory. You get the first set of equations, which are Einstein equations as usually. I mean, curvature equals energy density in a sense. I mean, the Ricci tensor minus 1/2, etc. Ricci scalar is 8 pi j times the stress energy tensor. So that's what I'm calling the usual Einstein equation. But you have a second set of equation. So the first set of equation involves curvature. But if you have torsion, you have a second set of equation. And the second set of equation is an equation for torsion. And the source of torsion at the right-hand side, at the matter side, is the spin density, really the spin density. So this, I think, answers partially to your question. This is not the angular momentum density, but the spin density. And this is a reason why, at least this is what astrophysicists claim, this is a reason why there is no way up to now to know whether we really live in a space-time with torsion and curvature or with only curvature. Because you have to imagine an astrophysical object, because of course these are tiny effects in gravitation. So you have to imagine an astrophysical object which has a macroscopic spin density. And the spin, of course, is dipolar, and macroscopic objects usually have no spin at the end. So you have to imagine, for example, a neutron star with only polarized neutrons inside, giving rise to a big macroscopic spin of this number of neutrons. And then you would see the effect of torsion. But in the theory, this is done already. I mean, there is a coupling, like the coupling of curvature to energy, there is a coupling of torsion to spin density. And it cannot be observed in the case of astrophysics or cosmology, as I said, but it can be observed in effective theory in condensed matter physics. And for example, Elena was very nice to remind that I've made a few things on DNA, etc. And that's in that spirit. When you look at a chiral molecule, a simple molecule in the shape of a helix, in DNA you have the bases, and the bases have carbon or other or nitrogen atoms which carry the 2pz orbitals. And the 2pz, due to the helical structure, I forget about the double helix, a single helix is enough. But due to this helical structure, you have the pz which are doing this. I don't know if you see my hands, but I mean which are reproducing the helix. And then the hopping of the pz electrons, 2pz electrons from one basis to the next is following this. And when you have a helix, this is an example of something which corresponds to one-dimensional manifold with torsion. And the consequence is that it couples to the spin, and you can produce polarized spin current along the helix. And this is something that experimentalists observe. People in biophysics are producing polarized spin currents which are much, much stronger than people who are doing magnetoresistance or this type of things. So this is not, of course, in the context of the real field theory in astrophysics, but this is an effective realization in condensed matter, or even in biology in that case, where what you say happens, a coupling between torsion and spin. Mm-hmm. Now it answers only a part of what you said, because what you said was more difficult. You were also mentioning the momentum, the angular momentum of the field itself.
Yes.
And so that's true that in the case of Maxwell, we know how to do this, but as far as I remember, the decomposition is not gauge invariant. There are
there's a problem to separate these two, but it's clear what the spin of the photon is.
Exactly. Yeah. So that's a very, very interesting question. I think we have to do that for Calb-Ramond. I'm not sure that this is easy. The polarization states are much more difficult because this is not a single index, this is a two-index gauge vector. So probably more similar to gravitational waves from that point of view, the polarization states. But that's a very good idea. At least I have to put it on the to-do list. And since it will be too difficult for me, I will forget. But thank you very much.
Okay, pleasure. Thank you.
Thank you. I see that Irko would like to ask, but I'm sorry, just I would like to very short question, because about DNA. I would like to say that, as you know, in mostly DNA is a left rotation, but not right rotation. So how it can be linked? There is some idea why it's asymmetric. So.
No, this I don't know. I remember long time ago, some papers which were so I don't remember the details, but some materials in life are left oriented and some others are right oriented. But and when we do this in the lab, we obtain both. But in life, yeah, it's either one or the other. So that's something very. It seems to be a spontaneous breaking of symmetry somewhere in life. And what I would say, I'm totally ignorant, but I remember a paper long time ago in 80s or 90s in Soviet Uzbeki physics or something like this, which was saying that in fundamental interactions, the only place where you have this breaking of right-left symmetry is with the weak interaction. Because electrodynamics, gravitation, and strong interaction, all of them preserve PET separately, etc. Only the weak interaction doesn't. So only the weak interaction is the source of this. This is also why Feynman, for example, said that if we want to communicate with some people outside in a different galaxy, and we want to tell them to define what is the right and what is the left, there is no way, except if we use the weak interaction. So you look at the beta decay and you look at the neutrino from, let's say, backwards, and it is turning that way. It has LSCT that way and not that way. So I remember an old paper which was saying that the only candidate could be the weak interaction. So I don't know about weak interaction in life.
Yeah.
Another story, because weak is probably weak, but But that's true, that the chirality in life is imposed. Yeah.
Okay, thank you, Bertrand. Yeah, so please, Jurko. Yeah.
Thank you very much. In life, we have the strength of the weak ties, as we know in sociology. In fact, you started. Thank you very much for your presentation, for your talk. You started already to reply on what I was going to ask when you were replying on Reinhardt's question, but maybe you can specify what I want to know. So, if this space-time possesses torsion, and then if we consider the motion of the free particle in this torsed space-time, what kind of new effects could you expect? In a way, you already told that it is almost impossible to observe it on the large scales. But a hint, could you give me a hint? What would happen in this life?
In fact, you know, we learn in Euclidean geometry, we learn that the shortest path, trajectory between 2 points is a straight line. So the shortest is the straight one. In gravitation, we say the same. So of course, this is not straight in the same meaning, but we say that the shortest, the geodesic line, is the shortest. It is straight in the sense that this is the one along which you have parallel transport of the tangent. So this is what we call autoparallel. So autoparallel is, in a sense, straight, but in this curved spaceline. Okay, but these are two things which are different: shortest in length and autoparallel. When you have torsion, you have, of course, shortest lines, you have autoparallel curves, but they do not coincide. They're not the same. So that should be a possibility to make a distinction. There is an absolutely wonderful thesis. Okay, if you're interested, I could try to find it. Someone from Manchester, I think, I don't remember his name, but I have it somewhere. Where he makes illustrations of the geodesy. It takes the example of the Earth and considers someone going from Manchester probably to I don't know where. Okay, it doesn't matter. And of course the geodesic, we know in a sense at the line which is followed by aircrafts in these transatlantic flights, etc., etc. And then he says, and what about autoparallels? So when this is Riemannian geometry, this is the same. That when this is torsion which exists somewhere, he shows that the autoparallel can be almost arbitrary. So that's something which is which could be a possibility to find the difference between the two approaches, the two presence or not. Yeah.
Thank you.
You're welcome.
Okay, again, Ralph, I think.
I have only a short question to this point. I mean, you showed the Schwarzschild space. So there has this torsion something to do with spaces where you have rotation. For instance, the geometry of a rotating mass. Then you have something which I could consider as it distorts the space.
Yeah, in fact, not.
I think it's too simple, my understanding.
So. Yeah, in fact, I think not. As far as I know, for example, the Kerr black hole, which is a rotating black hole, has no torsion. So torsion, when there is a rotation, you have a coupling essentially between the time component and some of space, an angular space, at least one angular space component. Yeah. And but this is still purely curved space-time.
It's really like
some other
elastic torsion in
space. Yeah, you need to get a twisted. We say when there is torsion, usually we say twisted. So to get a twisted space-time, you know, again, I will take my. Do you see my sheet of paper? So here it is curvature, or in fact, not really curvature. It is a cylinder, but okay. And torsion is really doing this, you know.
Yeah.
I don't know if you see what I'm doing.
Yeah, I see.
This is very violent, and there is a singularity, and that's. So you need more, and the best example is the screw dislocation from that point of view.
Yeah.
And Bertrand, in this case, I'm sorry, just for this question, I'm sorry. If you say the Burger's vector for the screw dislocation, can you estimate the amplitude of this Burger's vector? What it should be for the given object?
I think that in cosmic string there are that should be okay. I don't know the answer, but I think in Vilenkin is a specialist of cosmic strings. I think he gives numbers because he's very, very interested in trying to find possible proofs of the existence of the cosmic strings. So there are essentially two quantities which define the cosmic string. One is the linear mass, the mass per unit length, and the other is the stress energy tensor along the direction of the string. And for a standard straight cosmic string, both are equal. This is why it is straight. But for the wiggly string, for example, they are not equal. So there are some people who are really looking at numbers to see whether it is feasible to observe these objects or not. And as far as I know, the next generation of gravitational detectors, so not LIGO and Virgo, which are specially dedicated to black holes and neutron stars, but I don't remember the name of this detector, which will be in space with satellites, etc. But this one, in principle, should be able to detect events coming from crossings of cosmic strings, etc. So for sure, there are people who know these numbers, and but these are tiny numbers, of course. Really.
Okay. Thank you. I'm sorry I interrupt your discussion. Please,
Thank you. I am finished, so to say.
So thank you very much for both lecture today. It was very exciting lecture, and it was very exciting final description about maybe we will find in our space have some torsion. And
many thanks to the chairpersons and to all attendees of today's meeting, and looking forward to meeting all of you tomorrow.
Okay.
Thank you very much.
Yeah.
Thank you, Jurko, Rainer.